Hey there, welcome to the Teaching Decimal Operations video. This is teaching decimal operations without just teaching the rules. So what we'll cover in this lesson is why I teach decimal operations without the rules to start with, and then teaching each of the operations, addition, subtraction, multiplication, and division, just a brief overview of each of those. So how often have you found that your middle school math students or your upper elementary math students make procedural mistakes and errors even though they have learned the rules? Or maybe they've even learned some little tricks to help them remember the rules, but they make mistakes because they mix them up. I taught decimal operations for more than 20 years, and I've seen over and over students who know how to add and multiply decimals, but then follow the wrong rule for the operation that they're completing. In sixth grade math, again, students know there are rules, but they end up asking themselves things like, do I line up the decimal points when I'm adding or when I'm multiplying? Or do I jump the decimal point over when I'm adding and subtracting, or is that when I'm multiplying? What if there's no decimal point? What do I do then? They don't remember when to use which method to place the decimal point in their answer. So there are all these things that they have learned, but they still don't remember which rule applies to which operation. So a while back, I decided I did not want to talk about the rules for where or how to put the decimal point or how to set up the problem. I wanted to focus on logic. And so I started asking my students to solve this particular problem and then explain to me why their answer made sense. So I just gave them this problem at the start of our unit and asked them to solve and tell me why it made sense. And so here are some of their answers and their reasons. And again, this is before we went through anything. This is based on their previous year's knowledge. So we got answers like, this number makes sense because I tried my best. And if I remember correctly, addition problems, you don't need to line the decimals together. Or this makes sense because when I added, I knew that it doesn't matter how it's lined up. Or 78.42, I added 9 and 2, and then 1, 8, and 5. Next, I added 1, 3, and 7. Finally, I added 7 and 0, and I put the decimal in the middle. 7.841 makes sense because with adding, you only have to add the decimals on top. Then you add and finally add the decimal back in. 426 and 89 hundredths because I put the decimal point 4 spaces back because there are 4 numbers behind it. And 7 and 841 thousandths makes sense because you add like normal and then take the decimal from the farthest out and put it with the answer. So as you can see, these students believed they were doing the right thing based on what they believed they had learned, but none of these answers were correct. And they all thought the answers made sense because they followed what they believed was the right rule. Even for students who did find the correct answer, their reasoning wasn't based on logic. So here are a few of those answers. 42 and 689 thousandths, this makes sense to me because this is how I learned it. You do simple addition, but line up the decimal points. So correct rule, but it only made sense because they were following the correct rule. This makes sense because I used what my 5th grade teacher taught me, line up the decimals, add zeros, so everything is lined up, and then solve. I don't know how it makes sense, but it's how I learned to do it. So again, they got the correct answers, they followed the correct rules, but they didn't really have any other reason for it making sense. Of the 126 grade students in my math class, only 8 said the answers made sense because 35 plus 7 is 42, or because I estimated, or when we're doing addition, we know we end up with a bigger number. So at least there was a little bit of logic there. So what's the point of teaching the rules, especially to the middle school students and upper elementary students who might have a little more difficulty in math? If they can't remember the right rule, then they can't tell if their answer is reasonable or not. They need to develop their number sense and they need to develop an idea of what is reasonable. And the way that we've worked on that in the past is to start with estimation. What's the purpose of lining up the decimal points when we're adding and subtracting decimals? And what do we do if the numbers don't even have a decimal point? I know some students get pretty lost when that happens. Lining up the decimal points helps us line up the place values so that the place values are added with or subtracted from like place values. If students don't understand the point of lining up the decimal point when adding or subtracting, they may have missed the idea that we're trying to line up the actual place values. So because I kind of believe students don't understand that point of lining up the decimals, I teach them to add and subtract by doing the following. First, identify the whole numbers in the problem and add them or subtract them to get an estimate. If necessary, students should circle the whole numbers. So in a problem like 3 and 45 thousandths plus 21 and 6 tenths, we would circle the 3 and circle the 21. And I know it's closer to 22, but if we get students to just focus on those whole numbers, don't worry about the rounding, just focus on the whole numbers to get a general estimate, that will be helpful to them to begin with, to those who have difficulty. So we would end up with an estimate of 24. And then to set up the problem, students line up the whole numbers according to their place values. So you have ones place lined up with the ones place and the tens place with the tens place. And if those whole numbers are lined up correctly, the decimals will automatically be lined up. And then when students have a problem like 50 minus 9 and 625 thousandths, lining up the 0 and the 9 in the ones place will put the decimal numbers in the correct place. And it will make it more obvious where that new decimal point is going to go after the 50. Step 3 is to add a decimal point if needed for the whole numbers, and then annex zeros so the decimal point of the numbers have the same place value. So now we've got both numbers going to the same place value and we have our decimal points lined up with each other. So then students complete the operation, adding the digits in the different place values. And then they need to add the decimal point where it seems reasonable, and that's where the estimate is helpful to them. So if we look at the estimate that was 3 plus 21, then we stop and think, where should the decimal point go to be close to 24? The only logical place there is between the 4 and the 6. Now for the student who forgets when the decimal point in the answer is supposed to line up with the one in the problem, or forgets if they should count the number of places behind the decimal point, which rule are they supposed to follow? Those students who were trying to follow a rule and may have forgotten about which one was working may have placed the decimal point after the 2, or they may have counted all the places behind the decimal point and decided there are 6 places, so I need 6 places behind my decimal point in my answer. Neither which of these are reasonable. But if they stop and think about the fact that they said 3 plus 21 is about 24, it makes them stop for the moment, really think about it, and then place the decimal point in the spot that makes it close to 24. And conveniently, it's nice and lined up with the ones that were in the question. Now, the more we incorporate the estimation like this and relate that final answer to that estimate, the more often students will think about what seems reasonable. Let's finish up that subtraction problem, 50 minus 9 and 625 thousandths. We can look at this as an estimate and say this is 50 minus 9 is 41, and students don't have to worry about the rounding. Or if they want to round that up to a 10 and say 50 minus 10 is 40, that's fine. Either one is okay. They're very close to each other. Now we did line up the whole numbers on the previous slide, and we did annex zeros. So we just need to subtract and then place the decimal point. So we subtract here. And then thinking about that estimate of 41 or 40, with either estimate, the logical place to put the decimal point is between the 0 and the 3 for an answer of 40 and 375 thousandths. What do you think? Do you think students can make more sense of adding and subtracting if they estimate first and think less about what the rule is? Okay, let's look at multiplying decimals. Now, estimating the answers to decimal multiplication can definitely be more challenging. Problems like 23 and 5 tenths times 4 and 428 thousandths would not be as bad because there are whole numbers involved. And here we could use compatible numbers of 25 times 4 and get 100 as an estimate. Then when placing the decimal point in the digits that they would get as the answer, students can place it so the answer is about 100. Not 10, not 1, not 1,000. So there are definitely a lot of options for placing your decimal point here, but we know it's supposed to be about 100. The only logical place to put it is after the 4. Before we get too far into multiplying with students, I think it's important to do a little bit of exploration to see if students can find any patterns in their products. Estimating, again, can definitely be challenging, but if students can recognize some patterns, it can help with their estimates. So I like to have them first think about whether they should expect their answer to be more or less than the factors they started with. And we did a similar exploration to this in the fraction multiplication and division modules in the course. I give students problems like these, and I would normally let students use calculators to find the answers here because the focus is not on the calculations. I want them to get the answer quickly so they can spend more time thinking about those products. They find the solution to each problem, and we ask them to make some observations like these. Describe the way the products change from the top of the list to the bottom of the list. Why are they changing in this way? What happens when you multiply a decimal number by a number greater than 1? And what happens when you multiply a decimal number by a number less than 1? And then test out your ideas with a few other problems. Again, this activity, just like when we did it in fractions, gives them a good framework for creating some of their own rules that will help them when they're estimating, which of course we would discuss together. And hopefully students will come up with rules like these. Multiplying by a number greater than 1 gives an answer greater than the factors. Multiplying by a number less than 1 gives a product less than the multiplicand. And the smaller the multiplier is, the smaller the product is. If they don't find these on their own, then certainly we would guide them and discuss them and then test these out with some more problems to make sure that we can prove that these do work for various problems. After exploring and finding some patterns, we can then talk about estimation with the students when it comes to multiplying decimals. And I do think the estimates can be very general to start with. We're really trying to get students to recognize whether their answer is in the right ballpark. So let's look at a few examples. We've got 15 and 1/10 times 1 and 3/10, and to estimate, we could say that's about 15 times 1. It's very general. If students think back to the exploration, they might be able to say that the answer should be more than 15 because we are multiplying by a number that is a little bit more than 1, but we should at least be in the ballpark of 15. 10 and 9/10 times 8/10, we can say that's about 11 times a number less than 1, but it's close to 1. So thinking about our exploration, if we're multiplying by a number less than 1, our answer should be less than 11, but pretty close to 11 because, again, 8/10 is pretty close to 1. So we almost have one whole group of 10 and 9/10. 75 hundredths times 213 thousandths. This is a little bit tougher because these are both decimal numbers. We don't have any whole numbers to work with. So we could say that this is about 75 hundredths times much less than 1, a number that is definitely a bit smaller than 1. So we have something that is also, it's kind of close to 0. It's not too far from 0. So our answer should be much less than 75 hundredths and maybe a little bit closer to 0 because we're multiplying by a number that is very small. Again, that's very general, but when we look at what our final answers are and students think about where's the logical place to put the decimal point based on knowing that we have to have something that is smaller than 75 hundredths, I think that general estimate is helpful for them. Step number 2 in multiplying the decimals would be to set up the problem like a regular multiplication problem, not worrying about annexing zeros or lining up the decimal points or anything like that. Just set it up as a regular multiplication problem. Step 3, we complete the operation, multiplying just like whole number multiplication, and there's no need to add decimals in the rows. I know sometimes students seem to want to add decimals in the rows, but no need for that. And then for step 4 is to add the decimal point in the answer using the estimate to help. So looking at the first one, 15 and 1/10 times 1 and 3/10, Our general estimate was 15, really more than 15 because we were multiplying by greater than 1. And so when students take a second and look at 1963 and think about where the decimal point could go so that it is relatively close to 15, we can take them step by step and say, if we put it before the 1, is that logical? So we have a completely decimal answer. No. If we put it after the 1 and we have 1 and 963 thousandths, is that close to 15? Not really. If we put it after the 9 and we have 19 and 63 hundredths, is that close to 15? Yeah, that's pretty close to 15, and it's more than 15. And we can still check 196.3. Is that logical? No. So it helps to talk them through that and let them see and let them test out the different places that the decimal point could go to make us have an answer that is close to our estimate. The next one, 10 and 9 tenths times 8 tenths. We said our estimate was less than 11, but kind of close to 11. So thinking about where would the decimal point go here, if we put it before the 0 or before the 8, in both cases we're talking about a number that is less than 1. If we put it after the 8, then we've got a number that is less than 11, but it's pretty close to 11. If we went it after the 7 and had 87, that's definitely not close. So the only logical place here is after the 8. Now the third one, much less than 75 hundredths, closer to 0. This one's a tougher one. We could think about putting the decimal point before the 0. That would give us a very, very small number, definitely, close to 0, definitely less than 75 hundredths. Or we could put it after the 0, also a very small number and less than 75 hundredths. After the 1 or after the 5 or the 9 or the 6, then we know that it is definitely getting too big. So our options would be before the 0 or after the 0. And that one might be tough for students. It does go after the 0, so our answer is 15 hundredths, or sorry, those two places gives us 15 hundredths. And I think as students get more familiar and understand more the size of the numbers, putting it before the 0 would help. They would realize that is a very, very small number, much smaller than we need. So this one again is a little tougher, but I think helping them talk through some of these and get some experience with some of these and thinking about the estimating is definitely helpful. We could also help students estimate by thinking about benchmarks. We'll just look at a quick one of those. For a problem like 23.5 times 0.7, we can help students think about the idea that 0.5 is half, and half of 23 and 5 tenths is pretty close to 12. Half of 24 is 12, so half of that would be close to 12. So 7 tenths times 23 and a half should be between 12 and 23 and 5 tenths. Now that's a huge range, to give them that as an estimate, but it should be closer to 12. It should be between those numbers. So the general estimate is pretty big, but when the students get the digits of 1645, the only logical place to put the decimal point then to get into that estimated range is between the 6 and the 4. Putting it after the 1 just gives us 1. Putting after the 4 gives us 164, and neither of those are reasonable for what we thought about. So the logical place is after the 6. I'll put it up here at the top. 16 and 45 hundredths is the answer in there. So just another quick thing to think about. We could definitely go into more depth about that if you wanted to. On to dividing decimals. I think this is, of course, difficult for students, challenging, but still good to think about. Taking an exploration like we did with multiplication. Having students think about the rules. Should we expect the answer, the quotient, to be more or less than the dividend? That's really important for them to think about. And so we can go through this in the same exact way. So we've got all the answers, which again, I would have them do on the calculator so that they can get those and not worry about the calculation part of it. And then ask them again to describe, how do the quotients change from the top of the list to the bottom of the list? And why is that? Why are they changing in that way? If we look at the top, we've got 20 and 5 tenths divided by 2, giving us 10 and 25 hundredths. And down here, we've got 20 and 5 divided by 500ths, giving us 410. Very, very big difference between those answers. Why is that? What happens when you divide by a decimal number greater than 1? What happens when you divide by a decimal number less than 1? And again, give them time to think about those and maybe test those ideas with some other problems. Students, again, hopefully will come up with some things like dividing by a number greater than 1 gives an answer less than the dividend. Dividing by a number less than 1 gives an answer greater than the dividend. And the smaller the divisor is, the greater the quotient ends up being, of course, because we're fitting more of those little groups into that dividend. After the exploration and finding some of those patterns, we would again talk about estimating. And again, I think the estimates can be very general to start with. We're really trying to get students to recognize whether their answer is in the right ballpark. And of course, some are going to be more difficult than others, but the more we focus on looking for the reasonable, the better they will become at doing that. So we'll look at 16 and 3800ths divided by 2 and a tenth. That gives us 16 divided by 2 as an estimate. We get 8, which is less than the dividend, and that follows the pattern that we talked about. 12 and 2/10 divided by 8/10 is 12 divided by less than 1, but it's pretty close to 1. So thinking about the pattern that we just went through, the exploration, since we're dividing by something less than 1, our answer should be more than 12.2, but pretty close to 12 because it's pretty close to 1. 7500ths divided by 1500ths. We're talking about 7500ths divided by a number much less than 1 and a number that is fairly close to 0. So that number is pretty small. So we should, to be very general, end up with an answer that is more than 7500ths. Could be significantly more because we're dividing by a fairly small number. Okay, so we set up the problem like a whole number division problem, and then we move the decimal points. So first we make sure that we have this set up correctly with the right number inside the little division house. And then we move the decimal points in the divisor and the dividend. We move them the same number of places. So we now have a whole number in the divisor. In step 3, you would complete the division just as you would complete whole number division. And I'm just going to add the answers here instead of adding all of the steps. And then you would add the decimal point in the answer using the estimate to help. So the first one, our estimate was about 8. And so we've got a 7 and an 8. And the only logical place to put the decimal point so that our answer is about 8 is 7.8, putting it between the 7 and the 8. If we put it before the 7, we have 7800ths. If we put it after the 8, we have 78. And neither of those are reasonable to match our estimate. The second problem, our estimate was more than 12, but close to 12. And the only logical place to put the decimal point here is between the 2's. If we put it before the first 2, our answer is 1 and something. If we put it after the second 2, it's 122. So conveniently, the decimal point is lining up basically with the decimal point in the problem. And students may notice that if they did put their digits in the correct place in their division problem, in their work. And the last one, we said the answer should be more than 7500ths. And the only place we can put a decimal point so that it's more than 7500ths is after the 5. If we put it before the 5, we have 5/10ths, and that is less than 7500ths. And so there we have it. We have that estimating with the decimal division. Okay, in this video, we talked about why to teach the operations without the rules to start with. Now, I would end up talking about the rules after we have gone through this, after we have worked with the estimation, after students get comfortable recognizing what is a reasonable answer. We would talk about the rules and perhaps let students work on discovering their own rules and writing their own rules in conversation with us, of course. And then we talked about each of the operations briefly and shared some examples of estimating with those. If you have any questions, please feel free to put a question in the discussion here on Thinkific or email me or put something in the Facebook group. Okay, take care.